Okay, we're looking at chapter 15 today, which deals with a little bit more with our equilibriums, more specialized. We're going to be looking a bit at solubilities. Now, in the past, we looked at the term of solubility in absolute cases, as in always soluble or never soluble. Well, it turns out that's not entirely true, because calcium fluoride, which is something we predict to be aqueous, we actually can get it to actually form or precipitate, even in water, and by mixing with things, you get these interesting colors. But what we're going to look at is something kind of interesting. We're going to look at something we know is not soluble, something that we said way back in Chem 1 was definitely going to be solid if it gets into solution. Turns out that's not entirely true. If it were to react, it would actually make some silver ions aqueous and some chlorine ions. It just turns out this one has a K that's very, very small, which means it doesn't go forward very much. But it does actually dissolve some. It's just very, very small. And even things that we said in the past were always aqueous, sodium chloride for instance, has just a large K. It actually does have an upper limit. Now it's really high. Turns out for sodium chloride it's something like 380 grams into a liter of water. So it does take a lot before it gets to the upper limit. But it turns out this always soluble or never soluble don't actually show us enough pictures, or doesn't explain enough. We should be using Ks to talk about the solubility. Alright, now that's interesting. So we're going to look at these, and the very first one we're just going to balance an equation for it. And then we're going to figure if we can figure out what the K would be for it. So calcium sulfate, because of the charge of the ions, would have a formula of CaSO4. And in equilibrium, it would turn into calcium ions and sulfate ions. These are both aqueous, and these are both, and this is a solid. So because that's a solid, our K for this will only have our products. I'm out of space. This says SO4. Alright, well, we don't really need that equation to come up with a K. We can skip right to it if we know the formula of our salt. So this next one, chromium, Cr3 plus, and carbonate, CO3 2 minus, would be chromium carbonate. Alright, it would have a K then, more specifically a solubility product K, that has just the chromium, and it would have 2 of those, and the carbonate would have 3 of those in the formula, and that would be the only thing for the KSP. And we can actually do that right away with this. So Mg is a 2 plus, OH is a -1. So we can go right to our KSP. We don't need to always write out that equation. Matter of fact, if we notice, the coefficients kind of multiply together like the ionic charge did. So I know I may need to put a 2 there to balance that out. Now the bottom one here, I have to do something kind of different with it, because arsenic being As3 plus and sulfur being 2 minus, you might immediately want to write down As 3 plus 2 and sulfur 2 minus 3. In this case you would be wrong though. Turns out S2 minus is a very, very, very strong base, and if I'm in water, it actually neutralizes itself. Water is is an acid enough in this case that it neutralizes some of that very strong base of the S, and we end up with all the S2 minus gets turned into HS and OH. So, because of this wonderful thing, this is never in a KSP. What we're going to do is for every single one of those sulfurs, though, we'll keep it there, at least the 3, but we're going to say it's an HS minus and an OH. Now there are other things that do that, but the only thing that only anion we have to worry about in general chemistry that does anything like this is sulfur S2 minus. Okay, now we know that, let's do something with it. Because the neat thing about playing around with solubility is you get some interesting things, like paints, for instance, which will transfer those beautiful pigments from that insoluble stuff that's in that liquid and just dries out and make pretty pictures like that. Alright, so let's play around with some ideas of what this is and figure out what a KSP actually is. Alright, so, or what it tells us. The interesting thing is, if I were to go to something like lead sulfate, which is a component in your battery, PbSO4, because of our charges, we would find a solubility of S equal to that 4.25 times 10 to the negative third grams per 100 milliliters. And that's typically how you see solubilities listed. There is a mass compared to a volume. And it typically is given both values. It's not like it's assumed to be 100 milliliters all the time. 100 milliliters or 1 liter are the common ones, but they almost always list both. What we want to do is turn that into a KSP. Alright, so what we know right now is the KSP for lead sulfate would look something like so. Just one of each. Now, all we need to do then is, if this is, if you see, if this is the solubility, this 4.25 times 10 to the negative third grams per milliliter, we're going to turn that into the molarity. Because technically, for every lead sulfate that dissolves, there is a lead and there is a sulfate. So we just need to take that S value and square it, but we're going to need to turn that S into molarity first. So I'm going to start with that 4.25 times 10 to the negative third grams per 100 milliliters. And first thing I'm going to do is convert our grams into moles. So we need the molecular weight of lead sulfate. Let's see. Lead has a molecular weight of 207.2. And a single sulfur, 32.06, and 4 oxygens. Get 303.3. And on the bottom, I need this in liters because I want moles per liter. So what I'm going to do is I'm going to get rid of this and put a decimal right there, because 100 milliliters is 0.1 liter. Alright, so the solubility is given in grams per 100 milliliters. We're going to use this to convert it into moles per liter. Alright, so we have a molar solubility of 1.4 times 10 to the negative fourth moles per liter. To turn this one into a KSP, we're just going to square that number, because it's S times S is our KSP. So our KSP in this case is 1.96 times 10 to the negative eighth. And just like any Ks, there are no units. Alright, let's do that again. Slightly more complex one. Got lead fluoride, which is one of those that back in Chem 1 we would have said was insoluble. But it turns out it's slightly soluble. 0.6 grams per liter. Alright, so we're going to do the same type of thing with that 0.6 grams per liter. We're going to turn that into moles per liter. So we're going to start with the molecular weight of lead fluoride. And lead is still 207.2 grams. And fluorine is 19. I'm going to get a molecular weight of 245.2. Didn't have to worry about anything on the bottom because that was already liters. Now, I'm not going to do anything with that math yet, because what I want to do is take the KSP equation for the lead fluoride and figure out how the S is going to apply to this. All right, because the S applies to how much of this dissolved, how much lead fluoride dissolved. So for every lead fluoride that dissolved, there is a single lead. But for every lead fluoride, there would be 2 fluorines going in there. So the fluoride is twice as much as the S. And it still is squared because it's squared there. So you will see this happen a lot. If there's a need to be, if that had been a 3 there, this would be a 3 and this would be a 3. So you're going to, looks like you're doing the same thing twice. You're going to use the same value twice. We're doing it for different reasons. But technically what we're going to do is plug this, figure out what this S is, and then plug it into this little equation here, get our KSP. So let's solve for our S. 0.64 divided by that 245.2 gives a molar solubility of 2.6 times 10 to the negative third. And we are going to, this will turn into 4s squared times s, so that'd be 4s to the cubed. So we are going to cube this value and multiply it by 4. And we get a KSP of 7.11 times 10 to the negative 8th. Alright, one more. Gonna kind of go, from a different perspective. I didn't give you the solubility quite the same way, because I told you how much of a mass and a volume of just 10 milliliters. So pulverized and shaken. Alright, we are going to use those two values to figure out what the solubility is. Then we're going to convert that into molar solubility. So 1 mole of calcium fluoride this time. Let's see, what's the molecular weight of calcium fluoride? Calcium is 40.08. Fluorine is still just 19.00 grams. So calcium fluoride has a molecular weight of 78.08. And this needs to be converted again. And get rid of that 0. Alright, so we're going to do that math here in just a second. Our KSP in this case is calcium fluoride. In terms of S, for every calcium fluoride there would be 1 calcium and there would be 2 fluorines. So this turns into 4s squared times s, 4s cubed. So I'm going to solve for our s. I didn't mean to delete that. 1.5 times 10 to the negative 4th divided by 78.08 divided by 0.01. This is our s. We will cube it and then multiply it by 4. And we get a KSP of 2.84 times 10 to the negative 11th. That was the 11th, or was it 10th? 11th. Okay, let's go backwards. Let's say I give you a KSP and I want you to determine the solubility. Now, we're never going to actually have you calculate the solubility in terms of grams compared to volume. You'll always just be calculating the molar solubility. So it's always going to say that. That's going to save us a couple steps. It's still not trivial. Alright, so magnesium hydroxide would have a KSP equation that looks like this. In terms of the molar solubility, every single magnesium oxide or hydroxide that dissolves, there would be 1 sulfur and 2 OHs. So our KSP is going to be equal to 4s cubed, because this is going to turn into 4s squared. So 4s cubed. And that's going to be equal to 6 times 3 times 10 to the negative 10th. Gave us our K. We're just solving for s now. On my calculator, I'm going to do that with, start with that K. Divide by 4 first, And now technically I need to do a cube root. I'm just going to raise it to the 1/3 power. I get a molar solubility of 5.4 times 10 to the, I think that was -4th. -4th. And it's molar solubility, so even though Ks don't have units, this gets units of molarity. Alright, where this comes into play and what we're going to do to see the need for a KSP, because technically it's kind of weird. Solubility is a very nice thing to use. 1.5 times 10 to the -4th grams is not a lot of grams to 10 milliliters, but you have the ability to compare those values. A KSP is not nearly as beneficial. Where a KSP pays off, though, is in something like this. So barium sulfate is something they use to improve x-rays when you're getting like an upper GI. Ends up looking something like this when they x-ray it. So you drink that stuff, barium sulfate milkshake, and it will stick to the sides of your stomach and your small intestines, and they can actually map it out. Great for detecting like ulcers or things that are kind of active, so sites that move a lot. But turns out barium's kind of toxic. So to make it less toxic, they put it with sulfate, because barium sulfate is one of those that's insoluble in water. Has a very large KSP. What we're going to do, though, is calculate what the actual solubility is, the molar solubility of barium sulfate. So we're doing something like we just did on that previous page, previous slide. We know that barium sulfate's KSP should look like something like so, because 1 and 1. That makes the math here really easy, because this is going to be terms of S and S. Alright, but let's do this math and get this number. We're just going to do the square root to get our answer. And I get a molar solubility of 1.05 times 10 to the -5th molar. Alright, now even though that's a low number, it's actually borderline too high for humans. Barium actually can cause some bad effects, so we don't want the barium that high at all. So what they're going to do is add some sodium sulfate into it. What that's going to do is, since the solubility is based on the product of these two, we're going to make the product larger by adding some to this. So what we're going to do is take that same exact equation, where this is still S, but the sulfate is S plus 0.10 molar starting with. See how much larger that is? That's going to really shift this down. Alright, now this does turn into a polynomial, and yes, it is solvable like this, but we can also kind of assume, since it's a huge number compared to this, we're just going to assume that goes away, because the 0.1 is much, much, much larger. So 1.1 times 10 to the -10th, and then I'll just divide by 0.1. This would be my, oops, I didn't put the 1 in there, did I? My solubility is now 1.1 times 10 to the -9th. Now, if we'd solved this polynomial and just plugged that in and did a quadratic, we get that exact same one in this case, because this, it is really a huge number by comparison. But what we've done by adding some of this sulfate into it is we really shift the solubility to favor most of this is based on just sulfate. Now, we do this in wastewater treatment facilities too. It turns out most things are insoluble with sulfates and sulfides. So when they want to clean water and get the ions out of there, they put sulfates and sulfides in with them, and that precipitates them out. Matter of fact, when you go by a wastewater treatment facility, when you smell that rotten egg smell, you're smelling the sulfates and sulfides they've added to get rid of all these bad minerals. But they just do something like this, get enough of it in there, all that more dangerous stuff like the barium precipitates out, and now it would actually just pass through. And that's what happens here is they have it very shifted highly, so even though you're drinking something that's dangerous, it stays as a solid, and it eventually passes through the large intestine, through the colon, and right out. All right. Here's something else we do with our KSPs. Now what we have here is talking about calcium, which is naturally in water, and phosphate, which is naturally in water. When they get high enough, either by natural means or unnatural means, they cause mineral erosion. It's a very active thing they watch for around wastewater treatment facilities because calcium is something we find in our drinking water, and it comes out in large amounts when they're cleaning up with the wastewater treatment facilities. And it's naturally there, so it's not a big deal. But if there's something that makes it go higher, that's something to worry about. Same with phosphates. They're found from Mother Nature, so anything that when a farm is growing, phosphates are something that actually do get washed out. So these are both things that are natural. That's why it mentions the green river, or a given river. If it's naturally green from algae and life, it's going to have these guys in it. Alright, so let's figure out if these two being at 1.0 times 10 to the -9th concentration is high enough to cause a precipitation to occur. And all we have to do is take our K equation, KSP equation, and this is 3 calciums for every 2 phosphates, and plug these values in to get a Q, just like we did in previous chapters. And I like that that's 1.0 times 10 to the -9th, because this makes the math nice, because it's still going to be 1.0, but it's going to be 9 times 3 and 9 times 2, or 9 times 5, so this would be -45th. Alright, so we have a Q, 1 times 10 to the -45th. The K is much, much, much larger. Now, if you think about that, when Q was smaller than K, our reaction could still go forward. Well, all precipitation reactions or all solubility reactions, that means it's going towards the ions. So, this is a situation where no precipitation happens. We can still go higher on those concentrations. Alright, let's actually try a different one. This is a situation where we're actually going to try to clean the water up, or separate things. Alright, so we have 0.05 molar barium chloride and 0.025 molar calcium chloride. They're mixed together, so that's the concentrations of that mixture. We want to know what the concentration of SO2 we would need to do, how much sulfates we'd have to add to it to get one of those to precipitate out completely and none of the other. So what we're looking at is, all right, we got a test tube, for instance, that's just got water in it. And as you add sulfates to it, the one with the lowest KSP, the smallest KSP, the barium, is going to precipitate out. So down here would be barium sulfate, and still in solution is still the calcium ions. If you added too much, you'd have barium and calcium down here. Calcium sulfate and barium sulfate. And then this would theoretically be nothing but, this would be free of the barium and calcium. It's not going to be straight water because we've been adding probably like extra sulfates in there. Alright, but what we want to do is find out where this starts and then where this starts. Because it wants to know what concentration. Well, it's between these two. So let's calculate the higher end. Where do they both start to precipitate? Well, to figure that out, since we know barium precipitates first, we're going to figure out where the calcium starts to precipitate. So we're going to do a KSP for the calcium. Actually, you know what? I'm going to do this over here underneath this test tube. Alright, And we can plug in our KSP, and we already know what the calcium concentration is. It's 0.025. We're going to solve for the SO4 concentration. Alright, so what does this concentration have to be to get a precipitation to occur, get our Q to equal our K? We're just going to take that 2.4 times 10 to the negative fifth and divide it by 0.025, and we get 9.6 times 10 to the negative fourth. Alright, so if we get the concentration of the sulfate up to 9.6 times 10 to the negative fourth, everything, both the calcium and the barium, precipitate out. Alright, let's figure out where the barium starts to precipitate, because we know we need to get close to that. But this will tell us how close we need to be. So KSP for the barium sulfate is 1.0 times 10 to the negative 10th. The barium is 0.050, and we're going to solve for the sulfate here. Very similar ideal. 1.1 times 10 to the negative 10th divided by 0.05, and we see that this concentration, very low, 2.2 times 10 to the negative 9th. Alright, so what this means, the answer to this question, there isn't an answer. You're looking for a concentration of sulfate between these two. The closer you get to this one, the more likely you're going to have where all the barium precipitates out, because you're going to have the sulfate in so much excess. So even if you had an answer of like 9 times 10 to the negative fourth, that is just smaller than this, 9.6, so that would work. So we're looking for a number just smaller than this, or closer to this value but not larger. Because if you go larger at all, you're going to get some calcium to precipitate out. But if it's under that, just the barium precipitates out. Okay. Next thing we're going to look at is how acidity affects solubility. Now, using a strong acid, but it could be any acid, because really what's going to happen is the H pluses are doing something to our solubility. Alright, now we're going to see something kind of interesting. We're not going to do any situations at all where the cation gets affected by additives. Now, you can have situations where we put OH in there and they cause secondary precipitation. That's a little bit more complex than what we're dealing with right now. So we're going to focus on what the H plus does to the anions. And I'm going to write those together because I just want you to look at these and ask yourself, is there any reason to suspect one or more of these equations would do absolutely nothing? Yeah, this one is not going to go forward at all because HI is a strong acid. So adding acid to silver iodide will not do anything at all to the solubility. The solubility of silver iodide is unaffected by the H+. But both these other two, these are weak acids. So being that they're weak acids, the H pluses will take away a little bit of those anions, and if these go away, you should see an increase in solubility. So really, when you're seeing a question like this, asking about acid, look at that anion. If it's an anion of a weak acid, then acids can actually allow them to go away, and that should increase your solubility. Alright, last little thing we're doing, oscillating reactions. Now I have a video here, let me get it ready. Alright, now what this is, it's one I found on the internet. There are 3 solutions mixed together, and as you finish mixing them, you're going to see this go through color change. Now this is not trick photography, this is what it really does. Yellow, immediately blue. Now watch the blue. just constantly cycling through the colors. Technically, this is going to do this forever. Well, not forever. It's going to go on for about 20 minutes. Which might mean forever if I were doing this in a lab and said you have to sit there and watch until it stops, right? That would feel like forever. But it's going to do this until the actual chemistry comes to equilibrium. Now, what's interesting, the actual chemical process, I'm going to stop this. The actual chemical process looks kind of like this. It's a lot of multi-step reactions. And these are the elementary steps. We got some that are backwards and forwards. They got 2 different Ks. But most of these, they're only showing the one way they are predicted to go. Now, what colors you're seeing are based on the I- and the I2. One's yellow, one's blue. And you're seeing the buildup of those going and forming and dissipating. Now, interesting, when the reaction is all done, there won't be any I2 and I- found, or at least they're not supposed to be. Almost always end up with I2 because of most people, when they do the experiment, purposely set it up to produce extra iodine because it gives you a little bit better cleanup. All right, but this is a neat little paper I found. Somebody got a PhD on it. Now, if you look at it, this is where we get incredibly complex because d over dt, calculus meets our chemistry. But what this paper did is they monitored all the compounds, how they're being destroyed, how they're being made, and they actually have them all mapped out. And then they're just going to constantly monitor them as this reaction goes. And they actually did a full-time based on those Ks and modeled those maps. And you're seeing the color changes. That's what they're doing on this paper. Someone actually got a PhD on it. Now, we left it out of anything up to now and not try to explain it because that actually brings everything together that we've just seen. It has our reaction rates, has the equilibriums, it deals with competing elementary reactions. It's very, very complex. Now, we did get a chance to do this type of thing in Chem 1 lab. Hopefully you had a chance to try it. But it doesn't work so well because I purposely set it up to make sure it's easy to clean and save chemicals compared to some of the videos you can find on the internet. But there are other oscillating reactions out there. Interesting YouTube search, you can look. They got some pretty neat ones out there with different colors and such. Okay, last little thing we have in our Ks in general is complex ions. Now, complex ions are very interesting in how they behave. So, chromium, a highly charged metal, typically if we get it into water, it will surround itself with 6 waters. It'll organize those waters. That's how chromium is going to act like an acid with Kas. But in this case, what we have is we put something else in there. In this case, some ammonias. And technically, there's going to be 6 ammonias in this reaction. As this one goes forward, the waters get totally replaced with ammonias. Ammonia being neutral, the charge of this stays the same, but we'll see that sometimes the charge actually changes based on the complex ion that we form. Now, what is very neat about this, turns out those complex ions are always very large K, so these are almost always going to be drawn with one-way arrows. I mean, look how big some of these Ks are. Positive 20. I mean, our smallest ones are still at 10 to the 8th, or 10 to the 6th. They very much favor going forward, always. All right, where we take advantage of this is it's going to help us on solubility. So remember how our silvers were insoluble? So if you had silver and it bumps into chlorine, you're going to have silver chloride solid. And it has a very small K forming silver and chlorine. So the KSP is very small. Well, it turns out what we could do is take this silver chloride and add, heck, ammonia even, NH3 to it. And instead of actually having just this equation, we're going to form some silver complex. And this K for this equation will be that KSP multiplied together with the Kf, or some combination of them. And because the Kf is very, very large in most cases, we get a nice little shift. All right, let's see where we actually use this. Turns out cyanide, for instance, being a very toxic substance, can really screw up your body on just even a small amount. Because what happens, we have iron floating around there for hemoglobin. The cyanide forms a complex with the iron and takes the iron out of the picture, so it's not able to actually partake in the proteins anymore. Hemoglobin. So your body, your blood stops holding oxygen right. All right, let's look at how little this actually takes. So, and we're going to see how we do a math type thing. So what we're going to do is we're going to start with our iron. And we're going to see, all right, the cyanide gets in there. And it's actually just the Cn minus. So don't worry about the sodium really. That's actually going to displace all of these waters. So all these waters are going to come off. I have no idea why I put 62 there. 6 H2Os. And if you look here, the Cn forms FeCN6. I'm going to need 6 CNs. Alright, now, you notice this has a very large K, so this is very much going to go forward when that happens. Alright, but we're going to study how far forward it goes. Now, I'm not going to do this, it's kind of be like our ice tables before. But I'm going to do this in terms of moles, because I want to know how many moles of each of these guys are present. So I'm going to take that 25 milliliters over the 3.1 times 10 to the negative second to figure out how many moles of iron there are in this situation. 0.0255 times 3.1 times 10 to the negative second gives us 7.91 times 10 to the, I think that was negative fourth. Negative fourth. Alright. Going to do something with the cyanide as well. This should be a much larger number because it's 1.5 molar. So 1.5 times 0.035 gives us 0.0525. Alright, now we already said because of the size of this Q, or this K, we're expecting this to go very far forward. What we're always going to do in this case, we're going to just assume this is an excess, and you notice it's a huge number by comparison. Even though we're using the cyanide up 6 times as fast as the iron, this is definitely more than 6 times bigger than this. We're going to have this thing go to 0. That is the amount, that's kind of our X in these cases. So here, this is also going to go down, but it's going to go 6 times that much. Now, reason we say 6 times is because of that 6. So this is going to be up that much. And we're not going to really worry about the water, so I'm just going to ignore it. Alright, so we're assuming this is 0, at least for this change row, but it's not really. We're going to see how close to 0 it is, but we're going to do these other two numbers for real. So this entire equation, not KSP, KF, would have just the iron with the complex of cyanide all over, the iron with a complex of water, and the cyanide to the 6th equal to our KF. Alright, this is 7.91 times 10 to the negative 4th, and that CN number, we're going to have 0.0525 minus 6 times 7.91 times 10 to the negative 4th, and we get 0.04775. And we're going to plug these numbers in to our equation. So our KF is that 4 times 10 to the negative 43rd, and our FE is this 7.91 times 10 negative fourth. But I can't leave it like this because this is just moles. I need a concentration. And even down here with the iron, not the iron is X. With the Cn, it's 0.04775 moles, and we'll raise it to the 6th, but we need volumes on both these. Alright, but the volume's easy to get. We got 35 milliliters and we got 25.5 milliliters. So our volume is 25.5 plus 35. And we want these in liters, so 0.0605. Technically, we want to solve for that x. Now, I know this can be a complex thing, but I'm going to swap the x with the 4 times 10 to the negative 43rd, because that's something math will let us do. So I'm going to solve this by taking that 7.91 times 10 to the negative 4th, that top, divide it by 0.0605. Then I'm going to divide this by swapping the x and the 4 times 10 negative positive 43. So that does say it's supposed to be a positive. There's a positive up here. So I'm going to divide this number I just got by 4.0 times 10 to the 43rd. Also going to divide it by, in parentheses, the 0.04775 divided by 0.0605 to the 6th. Alright, that is the concentration of iron we'd suspect here. So, Fe H2O 6 3 plus concentration is predicted to be 1.35 times 10 to the negative 45th. Now, interesting thing about that number. If you think about the amount here, we're under a mole of everything present. This is less than a mole, this is less than a mole. That doesn't even work out really, technically, or arguably, to even 1 atom of iron floating around in there. Every bit of the iron is gone. There's probably not even 1 atom of iron that's truly available, because that concentration is a ridiculously small number, and we're even talking on the atomic scale that's smaller than a mole's worth of atoms. But that's typically what we see on these KFs. These KFs are typically very, very large, and they all go forward. And this is our trick, that change. You just take your metal and let it go to 0, and then base off your math based on it going to 0. Alright, another thing we can do with these KFs is fix some solubility issues. Alright, so old black and white film producing, you could actually use a chemical process. The film itself would have silver in it, and as that silver is removed, it would precipitate out with anything floating around in there. And that really is because silver is really, really insoluble. Alright, but that would create a problem when you go to develop it, because then you'd have a bunch of sand in there. So we're going to start by getting the solubility of just silver bromide. So we have the KSP of silver bromide looking something like so. And we can plug in our KSP right there and solve for the actual solubility. So 7.1 times 10 to the negative 7th molar. Alright, so molar solubility shows us that we're not going to get much silver in solution before we start forming a precipitate, which would be a problem in your black and white film producing, because you want to get rid of that silver. So what we're going to do is throw in some of this sodium thiosulfate in there. And the reason that's used is because the thiosulfate, which is the S2O3, forms a complex with the silver. We're going to see how that affects it in this problem. All right, so it's just a 1 molar solution, but what's going to kind of happen, that silver bromide doesn't very much go forward here because this is a very small K. That's that K with 10 to the negative 13th. What we're going to do to help that is we're going to take some of that silver that's in solution, let it form a complex with the thiosulfate. There's 2 of these. And that goes forward to give us this silver thiosulfate, which has a very large K, 10 to the 13th. Alright, so overall, what we would actually see is happening is the silver bromide with that thiosulfate, that should be a minus 2, forms Ag silver thiosulfate complex and some bromine, but the K is going to be these 2 together. So remember how if we add 2 equations together we can multiply our K's? So our K for this new process, 4.7 times 10 to the 13th times 5 times 10 to the negative 13th gives us 23.5. Now it's not as large as the K for like the forming the complex, but this does favor going forward. Alright, now this equation can still be related to molar solubility. What I mean by that, every silver bromide that dissolves would still make one of these, because there's 1 silver in it, and 1 of these. So our solubility now, this K is equal to the S times S. So take that 23.5 and take the square root of that. Just by adding that 1 molar silver bromide, we jacked our solubility up to 4.8 for the silver. Pretty neat, huh? Alright, now that gets used a lot. We actually end up using the formations for a lot of interesting ones. There are certain ones, I'm going to back up to this table. Some of these, a lot of the ammonia ones, actually create a little bit of a color. So they can actually use this to detect ions. There is one that's for lead out there, for testing lead in drinking water, that forms a complex and you see a color. Now it's not as useful for drinking water because the amount of lead that's in drinking water that can be toxic is well below the limits that we can visibly see that. But some of these other ones, you get some cool little color changes. Great way to test what's going on. Alright, that gets us done with this chapter.